A very good morning to all. Today we are going to discuss about a new topic, that is imperfections in solids. In our earlier classes we heard that liquids and gases, they are fluids because of their ability to flow. The fluidity in both cases is due to the fact that the molecules are free to move about. On the contrary, the constant particles in solids, they have the fixed positions and they can only oscillate about their mean positions. This is the rigidity of solids. And these properties depends upon the nature of the constant particles and the binding forces operating between them. And the correlation between the structure and properties helps in the discovery of the new solid state materials with desired properties. And we also heard about amorphous and crystalline materials, and about the property shape. The crystalline solids have the definite crystalline geometric shape, but in amorphous solids it has irregular shape. And crystalline, second point is crystalline materials, they have the sharp melting point and characteristic temperature, but amorphous solids, it is gradually softened over the range of temperature. And when we cut with a sharp edge tool, the crystalline solids split into two pieces and generated new surfaces. They are plain and smooth. But if we cut amorphous solids, they cut into two pieces, but it has irregular surfaces. And another point noted that in the crystalline solids, they have the definite and characteristic enthalpy of fusion, but in amorphous solids they do not have definite enthalpy of fusion. And crystalline solids, they are anisotropic in nature, but amorphous solids are isotropic in nature. And crystalline solids have the long range order, but amorphous solids are short range order. These all properties are we heard from our early classes. Now we are going to discuss about the imperfections and the quality of crystals. That is, it is the important point, that is the quality of crystals is very sensitive, that is influence on the structural and atomic deficiencies. That is, it may be the structural defects, atomic defects, all have the impact on the quality of crystals. Sometimes it may be point defects, impurities, or impurities, that means the extra atoms, extra ions, and it may be dislocations, grain boundaries and twinning. All have its own characteristics and it has a very good impact on the quality of the crystals. And in ideal crystals, the atoms occur regularly, that we know. It has without any defects or faults, that we heard from our degree classes. But in fact, there is no perfect crystal free from the crystalline defects. The ideal crystal does not exist even in the best crystal, that is, there is no ideal crystal in nature. The faults are an exemption to the periodic and systemic order of the crystalline network of the material. And the term defects in the solid state physics is meant to mean any deviation or any disruption in the regular lattice arrangement, and it has an important role in solid state physics. Let us see. Here we can see that there is a regular arrangement in this area, and also the regular arrangement in this area, but we can closely observe that there is a defect in here, also a defect here, 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 and it is a defect here also, here, and here. This also it has the defects here also. Okay, and in this defects, that is, we can see that there is an impurity atom in between the regular arrangement. That is, in between the regular arrangement there is an extra atom. We call it is a impurity atom. And in this figure, this is the dislocation. And here up to this there are 3 atoms, but there is missing of atoms and the connections. Here also from here we can see there is only 2 atoms in this row. So in this column it has 2 atoms, but up to this it has 3 atoms. There is something is missing, so it completely affect its regular arrangement. We call it as edge dislocation. And this is also an extra impurity atoms, that is a positive atoms, or we call it as positive extra ions. We may call it as self-interstitial atoms. And this here there is a vacancy, that is missing of atoms from this position. And here we can see that there is atoms, but it is compressed atoms. That is a precipitate of the impurity atoms. This darkened color shows that is the impurity atoms. So there is the compression or the precipitate of the impurity atoms of about 6 atoms. And in this case, here also there is a dislocation. It is the dislocation loop. Up to here we can see there are 3 atoms, but after this line we can see there is only the arrangement of the loop of 2 atoms. Okay, or we can say this is the loop of 5 atoms, this is the loop of 4 atoms, and up to this is the loop of 4 atoms. But here again we can see this is the loop of 5 atoms. So here we can say there is a missing of an atom. And in this case there is also the substitutional impurity atoms, but it has difference in the size compared with the home atom. But in this case also we can see a dislocation. This may be the line dislocation. There is extra atom coming in this region, or we can say there is missing of the atoms in this region. Okay, so all these defects have its own properties, and it is surely affect the regular arrangement of the crystals. Now we can go into the classification of crystal defects. These crystal defects can be classified into point defects, line defects, and surface defects. A point defects occur when the crystal periodicity is primarily broken at one lattice site or a few adjacent sites. it may be the coming of the extra atoms, or it may be the vacancy, and it may be Schottky defects, and or it may be the Frankel defects. That is atom if there is an vacancy, if a vacancy, and also these atoms coming into the interstitial places, we can call it as Frankel defect, or the vacancy of ions with the opposite charges we can call is the Schottky defect. Okay, generalized general case, we can divide these crystals into three: point defects, line defects, surface defects. And there is one more difference, is that volume defects. Okay, that we will discuss later. And the point defects, it is divided into vacancy, self-interstitial, impurities, Schottky defects, and Frankel defects. See, this is the image that's showing the vacancies. Here we can see missing, here also there is missing. So we call this defects as vacancy. There is missing of atoms from the regular arrangement of the periodic crystal. Okay, next is the atoms in the interstitial positions. So there is an extra atoms coming to the interstitial position of the, or interstitial sites of the regular arrangement of the atoms. This is the self-interstitial atoms. And next we can see this is an impurity, fully impurity coming from the external. So we can see that there is a size difference and also the entire different property. So there is an extra atoms or extra ions coming into the sites, regular sites, or it may be the interstitial sites. This is the regular sites and this is the interstitial sites. So these defects are come under the category of impurities. And next is Schottky defect. And a Schottky defect arises when equal number of cations and anions are missing from the lattice. So this is the, here we can see a missing, here also we can see a missing from the regular arrangement. Here we can see a cation missing, or here we can see an anion missing. And next we can see a Frankel defect. Here the missing cation sit into the place of the another position. So we can see here this is the Frankel defects. And now we can find what is the major difference between Schottky defect and Frankel defect. That is, in Frankel defect, that is before Schottky defect, that arises when equal number of cations and anions are missing from the lattice. But in Frankel defects arise when some of the ions of the lattice occupy interstitial sites, leaving a lattice vacant. And this Frankel defect generally found in ionic crystals when anion is much larger in size than the cation. But due to these defects, the density does not change in the overall composition of the crystal. And KBr, NaCl, KCl, they are all the examples of the Schottky defect. and ZNS, AGBR, they are also the defects of the Frankel defect. And again, once again I can say that is the Schottky defect. Equal number of cations and anions are missing from the lattice site. It is found in highly ionic compounds with the high coordination numbers where the cations and anions are smaller size, and density of solid decreases because there is surely the missing of the cations and anions from the lattice sites. So there is the density of the solids decreases. But in Frankel defects, a cation leaves the normal lattice sites and occupies an interstitial sites. So the density of the solid remains the same. Note that point. Here in Frankel defect, the density of the solid remains same. And Frankel defect found in ionic compounds with low coordination numbers and where anions are much larger in size than the cations. Okay. Up to now, we will discuss about the basic introduction of the defects. In the coming classes, we will detail about these defects. Hope you are all understand the basic introductions. Thank you.